Hi everyone, my name is Ye Yang. I'm a cloud software engineer at Intel. It is my great honor to have my presentation in this year's SDC conference. My topic name is Accelerating PMEM device operations in Ceph with hardware-based memory offloading technique. This page lists the agenda of this topic. We will first introduce the background and the problem. Then we will propose our solution. Then we will detailedly describe how to enable Intel's data streaming accelerator in Ceph. And finally, we have the conclusion. So the first part is background and the problem. With more and more deployment of non-volatile or persistent memory devices in data centers, CPU resources on the host becomes a bottleneck while operating on PMEM devices in application mode under high workloads instead of using traditional hard disks or SSDs. In this page, the right diagram uh, describes this situation. When the host is equipped with PCIe or such SSDs, when doing the I/O workloads, the host CPU says, "I'm fine to serve 20 virtual machines. My brother's SSDs, they have DMA capability and can help me complete the IOs, so I'm not very busy. But if we replace those SSDs with persistent memory devices, things changed. When doing I/O workloads, the host CPU says, I can only serve 15 virtual machines, and I'm very busy because there is no DMA capability is available from persistent memory device. The root cause is that data operations between memory and persistent memory is different from data operations between memory and device. In the later case, we know there is DMA or RDMA capability on the device, and the CPU will not be the bottleneck. But when we use CPUs to conduct the operations between memory and the persistent memory, especially the persistent memory has the persistency features, then there will be a lot of CPU resources used on such operations. So how to offload the work from CPU with offloading techniques while operating on persistent memory is a valid requirement. For example, cloud providers would like to utilize the important CPU resources in customer visible workloads. For example, they want the host CPUs be virtualized to launch more customers' virtual machines instead of using those CPU resources on doing storage workloads on persistent memory devices. And it has a similar issue when persistent memory devices are deployed in Ceph's OSD, for example, in bluestore or C-store. And we face the same issue related with the high CPU utilization. So how to solve this problem? This section describes our proposed solution. We propose to leverage some memory offloading devices. For example, Intel provides some memory offloading devices such as Intel I/O acceleration technology, IOAT, or Intel data streaming accelerator technique. Intel DSA is a high-performance data copy and transformation accelerator that can be integrated in future Intel architecture processors targeted for optimizing streaming data movement and transformation operations, common with operations for high-performance storage, networking, persistent memory, and various data processing applications. And the DSA can support the following operations, such as movement operations. For example, memory movement between memory and persistent memory, fill, compare, flash, or other operations. It will be available on the Ceph Rapids platform. So how to efficiently leverage those memory offloading devices? Sync, sync or async. If we integrate those devices in async mode, it means that the integration overhead is very low when we use DSA like memory offloading devices into applications. But the advantage will not be clear in CPU utilization reduction and the performance improvement while running those storage workloads are not clear. And the second choice is to integrate DSA-like devices in async mode. And we know that the integration overhead is very high. You need to modify the applications and replace the function calls. Uh, Replace the function calls originally used by sync mode and use the a synchronized interface with the function code and with the callback parameters. But there will be CPU resource saving and we can see the performance improvement for the workloads. So to demonstrate that our idea is practical, we provide our solution in Ceph. For example, currently we integrated Intel Data Mover library to drive DSA and accelerate persistent memory in Ceph. And this section describes the detailed work on how to enable DSA in Ceph. As is well known, currently there is ongoing work to leverage C* framework to construct a new store, that is C-store. So we will first introduce our work to offload operations on persistent memory in bluestore first. Then we will describe some derived platform related with C-store. So in phase one, we would like to offload persistent memory operations in bluestore first. And currently, we leverage Intel DML or IDXT library to invoke DSA capabilities to offload the memory movement operations between memory and persistent memory. And we have the following two steps to make this happen. The step one is that we firstly use the synchronized API in DML to offload CPU operations on persistent memory. And the expectation is that the functionality can work. And the following two patches are already merged, and you can see such a kind of code in Ceph's bluestore. And in step two, we would like to use a sync API in DML to offload CPU operations on persistent memory, and the expectation is that we should have some performance improvement and mitigate the CPU pressure. But due to current Ceph architecture, this work may not be easy. It is different with the applications which use SPDK application framework, because for applications developed by SPDK framework, it is already the threading mode is already optimized in async behavior, and it is very easy to leverage the async APIs in DML. And we also know that if persistent memory are used in Ceph, persistent memory devices can use with two modes when the persistent memory is is used in application director mode. We can see that if persistent memory is in AD mode, it can be divided into two usage cases, two kind of usage. One is FSDX, and the second is DX mode. In FSDX mode, the persistent memory device can be formatted as a block device, and the user can get block devices such as DV-PMEM0, and the users can create file systems, for example, ext4, BTRFS, or others on top of that. And when PMEM is formatted in DX mode, we can say this is a character device. For example, DVDX0.0. Then you can also operate on this character device, but you cannot construct the kernel-based file system. So we think that if persistent memory with AD mode is used in bluestore, we should use the DX mode instead of FXDX mode. Because for using FXDX mode on persistent memory, you need to use ODX choice to mount the device. Then you can use libpmem library with CPU to obtain the persistent feature provided by the PMEM device. Unfortunately, if you use DSA to offload such operations on persistent memory with such configuration, then it may not always work due to the current support of Linux kernel. It means that if you use old Linux kernel, it will not work. So we provide this PR 45609 to leverage persistent memory with DX mode directly. And with this mode, it can be very easy to leverage Intel DSA to conduct the offloading work, since there is no file system created on persistent memory. So this page also introduces what is Intel DML library. Intel Data Mover Library is an open source library to provide high performance data manipulation on Intel CPUs, and it can leverage Intel DSA work queues exported by the kernel to offload persistent memory operations. When there are Intel DSA devices available on the platform, you can use IDXT config to create the Intel DSA work queues. Then when Intel DML is used in application such as Ceph's OSD process, it will use diropen to open IDXT config library and leverage created Intel DSA work queues in hardware paths. And in bluestore configuration doc page, we can see how to use IDXT to configure Intel DSA work queues. And the async work is still in progress. And the plan to enable Intel DSA in async mode in bluestore can be summarized as we will change the current usage mode in pmem module. That is a pmemdevice.cc file. We will create a help thread like the approaches in kernel device module or SPDK device module. And then we will conduct the operations on pmem by CPU in async mode first. Then we will leverage the async APIs in Intel DML library to conduct the operations between memory and pmem with the async approach. And in phase 2, we will also offload pmem operations in systore. As is known, systore uses systar framework, and we will expect the good async behavior in system, then we will do the following works. For example, we can use DSA to offload some memory operations such as duecast, copy, or others. And we can also use DSA to continue the optimizations on persistent memory with the sync behavior under CSTOR's framework. And finally, this is conclusion part. In this presentation, we realize the overhead or bottleneck of CPU to conduct data operations between persistent memory while performing storage workloads. Because data operations between memory and persistent memory is different from data operations between memory and device. For the later case, there is DMA or RDMA capability provided by device, so the CPU is not very busy. So we need some hardware-based memory offloading techniques to offload the CPU work. For example, we can leverage Intel's IOT or DSA technique to offload the work from the CPU. And in this presentation, we also introduced our work to leverage Intel DML library to offload persistent memory operations by DSA in Ceph. In the next step, we will continue improving the performance on persistent memories via memory offloading engines based on Intel DSA. For the performance report, we may publish it later after SPI is launched. So this is all my presentation. Thanks for your attention.